right, guys, so let's see. Midterms are graded, as you guys probably saw because we sent some emails out. Average was 64%, which it's a little bit low. But I'm going to offer you guys some extra credit if you want to try and make up for that. So I already put up an extra credit assignment on WebAssign. It's actually to watch a YouTube video is how you get the extra credit. You just got to watch this video. It's pretty cool. Like I don't know if any of you guys have heard of the 3 Blue, 1 Brown series on YouTube. You guys know them? Yeah, they're freaking great. Yeah. So it's this mathematician, or actually it's a group of mathematicians, programmers, and animators who take math proofs and animate them, which actually shows, the really cool thing about it is it shows you concepts that I think were not even possible to be shown until computers came along, computer animation. Like I saw one video on Fourier series that I'd learned about Fourier series like 10 years previously, but I never actually saw the visual representation quite the way they put it. So it kind of offers a really beautiful, intuitive, elegant understanding of mathematical concepts. And the latest one that came out, the latest 3 Blue, 1 Brown video came out like a week ago, and I watched it and I realized it totally actually applies to one of the things I was just teaching you guys about complex numbers. Like, remember I did that example of the four roots of some number that were symmetrically situated on a circle in the complex plane? Well, the latest 3 Blue, 1 Brown video uses exactly that same concept, the so-called roots of unity. These are the numbers, the complex numbers, that if you raise them to the nth power, they give you 1. So obviously 1 is one of them, but then it turns out that there's n other of them, like symmetrically situated around the unit circle. So I thought it was kind of neat and timely that this video came out right when I was talking about this stuff. So if you guys go watch the video and answer the true or false question on the homework about it, you can get just 5 homework points just for doing that. So yeah, that's up on WebAssign. And okay, that's it. Any questions before we get to the math? All right, so continuing on with complex numbers, one of the last things I said was Euler's formula. So here, recall this guy, which we're going to need. It's a very, very important formula in math. E to the I x equals cos x plus I sine x. I still remember being tripped out the first time I saw this formula. I mentioned right at the end of class on Friday that like if x is equal to pi, right? So if you plug in pi here, cos pi is 1, sine pi is 0, so that's I times 0, which just goes away. And if you move the 1 to the other side, oh, sorry, I made a mistake. Anyone see it? Cosine of pi is -1. There's a negative sign right here. Okay, so anyway, if you move the 1 to the other side, you could write this as e to the I pi plus 1 is 0, which is cool because it just combines all the different constants into one equation. But, all right, so moving on from that, I want to show you some important consequences of Euler's formula, which is we can kind of invert it to get expressions for sine and cosine in terms of complex exponentials. So, all right, I'm going to write this formula one more time. E to the I x is cos x plus I sine x. Now, this is true for any real number x. In fact, I didn't prove it. It's actually even true for complex numbers. But we're going to have x be a real number. And if it's true for x, it's true for negative x. So e to the negative I x which is the same as e to the I times negative x, will be cosine of negative x plus I times the sine of negative x, or e to the minus I x is, this is the same as cosine, because cosine is an even function. Sine is an odd function, so that becomes a negative sine. And the reason I wrote this below this equation is because I'm now going to add these two. So this guy plus this guy, adding these two, I get e to the I x plus e to the negative I x is, well, the plus I sign and the minus I sign cancel out. So I just get 2 copies of cosine. So if I divide this by 2, I get a formula for cosine in terms of imaginary exponentials. Sweet. Okay, that's fantastic. That's going to be super useful. And if I could do it for cosine, I could also do it for sine, except now I'll have to subtract. So, okay, so let's, if I do this minus this guy, okay, then I'll get, so that'll be e to the positive ix minus e to the negative ix. And now the cosines cancel out. Cos minus cos is gone. I sine minus negative I sine. So I sine x minus negative I sine x, which is 2I sine x. And if I divide everything by 2I, I get a similar expression for sine of x. So it's 1 over 2I. And then it's almost the same as this, but with a minus right here. E to the ix minus e to the negative ix. All right. So some formulas in this class are totally worth memorizing, and these are among those. So yeah, I would say, yeah, memorize these 2 formulas. It's very useful. I'll show you some of the uses of them. Like, one of the things I was going to do, if I had had time to on Friday, was after writing these 2 formulas, I was going to tell you how useful they are. One of the things they're useful is for proving trig identities. So I was going to say, okay, someone give me a trig identity, any trig identity, and I'll prove it. I'll prove it. So that was going to be me being a show-off. And I still want to do it, but I don't think we have time. So just take my word for it that I could prove any trig identity. So, like, for example, sine squared plus cosine squared equals 1. Sine 2x equals 2 sine x cos x. Cosine squared x equals, 1 plus cos 2x over 2. And I could go on. Any trig identity you can prove if you just use these imaginary complex exponentials. It's kind of amazing. Like, I don't know if you remember the first time you had these formulas proved, but sometimes they had to use like geometry, and it got kind of complicated, and now all of a sudden there's a totally new way to do it where you don't even need to like look at a picture. Just mess around with the symbols and the formula just pops right out. So I will show an example of that in an example later today, towards the end of class. But for now, right now I need to switch gears and start on 7.2, which might initially seem like a separate topic. Kind of. You'll see how these are going to apply. So 7.2 is on trig integrals. And, okay, we're going to build on some stuff we already know, and we're going to do some new stuff. So let's start with something we already know, like the integral of sine x dx. Everyone knows how to take this antiderivative. What is that? That's negative cosine of x plus c. Not so bad. Okay. So now I'm going to start progressively making this equation harder and harder to deal with. So this is fine. This is good. No problem. How about sine squared? So this one, okay, have we done this in this class before? Hit some god hard, did you, this weekend? That's right. We did, in fact, do this in this class. So the trick that we used was it's actually a formula that's, okay, I didn't write the formula, but we have done this before in this class using double angle formula. Yeah, using the fact that sine squared is 1 minus cos 2x and over 2. These are all terms we can integrate, right? That's 1/2 times the integral of 1 minus cos 2x. So that's 1/2. I'll get an x. Integral of cos is sine. Okay, so we can handle a sine squared. It's a little bit harder, right? We had to use this identity right here. I just want to point out, you could also do it even if you didn't know this identity. You could just plug in this formula for sine and do an integral of complex numbers, which I will show you shortly. But for now, let's move on. How about to sine cubed? This is totally new. We have not attempted to deal with something like this in this class. So I now get to show you guys a new trick. And here's the trick. What we're going to do, we're going to make use of the following. We're going to need the fact that sine squared x plus cosine squared x is 1, and that d dx of sine x is cos x, and d dx of cos x is negative sine x. So here's the trick. I'm going to break this up into a sine squared times a sine. And then I'm going to use the Pythagorean identity to get rid of all the sines in this term and replace them with cosines. So this guy is the same as 1 minus cosine squared. So I get 1 minus cosine squared of x. And then I still have this sine x left on the end, which I deliberately left there because this is now perfect for what method is this now set up perfectly for? Good, u substitution, yeah. So this is the same as if I make the substitution that u is cosine of x, so then du is negative sine x dx. I get a 1 minus u squared. And then that's negative du. So let's put a negative sign in front and the du. And this is a nice, easy little polynomial to integrate. That's no problem, right? So that's negative u minus u cubed over 3. So that's u plus c. So that's u cubed over 3 minus u plus c, or what was u? Cos x. Cos cubed x over 3 minus cos x plus c. So the important new thing to learn here was the trick of taking the sine squared and replacing it by 1 minus cosine squared. All right, so remember that trick. Let's see. That was sine cubed. Let's go up to sine to the 4th. All right, moving on to sine to the 4th. Can I do the same trick here? Okay, yeah, it is sine squared times sine squared. If I tried to do, notice like the trick that I did here only really works if this is an odd power, right? Because you need to have a sine and then express everything else with cosine squared. So this, I'm going to have to do what I heard someone say, which is write it as sine squared times sine squared. Or here, let's just say, so this is sine squared squared. And I'll try to do the same thing that I did with sine squared, which is use the double angle formula. Yeah, okay, so that's the same as 1 minus cos 2x over 2 squared. So let's square this all. That'll be 1/4. Okay, I'm going to get a 1 minus 2 cos 2x, and then a plus cos squared of 2x. Did that help? Well, we know how to integrate 1. We know how to integrate cos 2x. What about the cos squared of 2x? Do we know how to integrate that? We do. Yeah, it's the same trick that we did with sine squared. We just used the identity that has a plus sign there. So this is 1/4, the integral of 1 minus 2 cos 2x, and then this will be 1/2 1 plus cos of 4x. 4x. Cool. Right, because apply the double angle, it's already a 2x, so now it becomes a 4x. Yeah?
What's the identity farther back there that shows that sine squared x is 1 minus cosine 2x over 2?
Yeah, that's the same one that I did right here. So that's a known trig identity, but since you asked, okay, I was really eager to do this. Let me just prove it using complex exponentials. So let's see what happens if I try to prove that sine squared x is 1 minus cos 2x over 2. And I'm just going to use this formula here. Okay, so sine squared of x, that'll be, according to this formula, 1 over 2i e to the ix minus e to the negative ix squared. Okay, so square this, that'll be 1 over 4i squared. And then squaring the inside, so e to the ix times e to the ix is e to the 2ix. Here, maybe I should show you guys this, right? So this is e to the ix minus e to the negative ix times e to the ix minus e to the negative ix. So I'll get an e to the 2ix. I'll get a minus. These guys are inverses of each other, so that's a minus 1. Same with these two. So that's another minus 1. And then that'll be plus e to the minus 2ix. So this, by the way, is minus 1. So I get a minus 1 over 4. E to the 2ix minus e to the negative 2ix minus 2. And if this is the formula for cosine of x, then, for example, cosine of 2x, you just replace all the x's with 2's here, is e to the 2ix plus e to the negative 2ix, which is, actually, sorry, I needed, wait, this is a plus, yeah, good. So this is actually 2 cos 2x, according to this formula. So the whole thing, I have negative 1 over 4, 2 cos 2x minus 2, which, let's cancel the negative signs. Cancel the. So I get 1/2 of 1 minus cos 2x. Cool. Who asked that one? That was you. What was your name?
Quinn.
Sorry?
Quinn.
Quinn. Cool. All right. So you satisfied, Quinn? Cool. All right. So yeah, you guys can see, like, you can prove, like I said, any trig formula. It's pretty easy. You don't even really need to think about it. You just need to make sure to keep on applying these formulas. So, okay. Back to the question of integrating sine to the fourth. Are you guys satisfied with this? I mean, I could finish the whole problem, but I think the point is that you guys see this is now a sum of terms that we all know how to integrate. So I'm not going to, in the interest of time, I won't finish this, but recognize you could now finish this. So let's continue to try making the problem harder. The next one is, how about sine x times cos x? So I'm showing you all these examples, and eventually you're going to start to see the general trend here. In fact, this one is kind of like one we already did. So this one is well suited for substitution via, like, u is equal to sine x, for example. So du is cos x dx. Which one do I want to do now? Okay, so that was pretty easy. How about sine squared x times cos x dx? What method can we use to solve this one? Another u substitute. The same one, in fact, yeah. Same, right? U is sine of x, so du is cos x dx. And the thing is just equal to the integral of u squared. So, in fact, continuing on in this pattern, sine to the nth power of x, as long as there's a cosine of x, all of these guys, we can just use this same method, right? Let u equal sine of x, and this thing will equal u to the n du, which is totally integrable. U to the n plus 1 for n plus 1 plus c, or sine to the n plus 1 x over n plus 1 plus c. Okay, good. We are rapidly expanding our repertoire of doable integrals. And you might notice, like, the sort of duality between sine and cosine. So similarly, the integral of cos to the n, as long as we have a sign at the end. We can do this one, same way, right? Except, well, I mean, almost the same way. Now let u equal cosine of x. So du is negative sine x. And, we'll get u to the n, a negative sine du. And so this is negative u to the n plus 1 over n plus 1 plus c, which is negative cos x to the n plus 1 or n plus 1 plus c. Okay. After doing all these examples, I think I've done enough that we can now confidently say we see the pattern and can do any combination of sines and cosines. Okay, so if n and m are positive integers, I think we've pretty much taken care of almost any situation that we can now handle. We can now handle this integral. So I'm going to write you a little flow chart of what to do here. Okay, so how about, I like it when, let's do if n is odd. So if n is odd, say n is equal to 2k plus 1 for some integer k. So this thing is equal to sine 2k plus 1 of x cosine to the m of x dx. So I'm going to write this as sine 2k x cos to the mx. I'm going to put one sign off at the end, which maybe you can, if you've gotten the picture, you see this is going to end up being a du after a u substitution. So I now use the trick that I showed you in my first example of this type, where I said this is the first real new thing you're learning. And that's to replace all these signs by cosines. So since sine squared is 1 minus cosine squared, this term is 1 minus cos squared to the k. Right? Because it's equal to sine squared x to the k. So that's 1 minus cosine squared x to the k. Here we've got a cos to the m, and then sine x dx. And now it's all set up for a u substitution. So if we let u equal cosine, then the point is we can solve it, right? We get 1 minus u squared to the k times u to the m du, which is just a polynomial. Potentially an ugly one, but, multiply it out, and you can do it. Okay. Now, that was if n is odd. If m is odd in this expression, we can do the same thing with cosine. So that only leaves one other possibility, and that's if both n and m are even. And that's kind of the most annoying possibility. Yeah, then you just got to like repeatedly use those double angle formulas. So that case is kind of a pain. Identities. So yeah, like cosine squared of x is 1 plus cos 2x over 2. And as we just proved, sine squared of x is 1 minus cos 2x over 2. All right, that pretty much takes care of all of any time you've got multiples of sine and cosine. And now let me make the problem a little bit harder. Notice like in all these examples, the arguments were just x. These are sines and cosines of the same frequency. What if I start messing with the frequencies though? Like instead of x, like what if I made it like a 2x and a 5x or something like that? That's actually pretty relevant for the something I already mentioned today actually. Fourier series and Fourier transforms are really useful mathematical trick which in fact a lot of you guys as engineers are going to have to get comfortable with. They're hugely important in like signal processing, acoustics, in I don't know, seismology, image processing. Anytime you're taking in a signal, which usually involves light and sound, light is a wave, oscillating electromagnetic field. Sound is a pressure wave. In both cases, it's a periodic phenomena and occurs at a certain frequency, right? Like you can hear me speaking to you at a certain pitch due to the frequency of the sounds that I'm making. And in Fourier series, you break down an incoming signal into its component frequencies. So I think just this second I was inspired to give you guys another extra credit assignment, which is to watch that other 3 blue, 1 brown video, the one on Fourier series. It's freaking awesome. You guys will trip out. I would show it to you here, except we just don't have time. So I'll let you guys watch that, from the comfort of your own couch.
How do you spell Fourier?
Fourier. So these calculations are, if you learn Fourier series, they're one of the first calculations you're going to have to do, is one like the one that I'm about to show you right now. So here'll be this example. Let's do the integral. How about sine of 2x and cos of 5x? Yeah. All of a sudden, all of the tricks that we've learned so far don't work. Not on this. Right? Like if you try and do a u sub, it doesn't work, right? Like if u was, sine of, 2x, then du would be cosine of 2x, which is not the same as cos 5x, so that doesn't help. So if you look at this in the textbook, they will show you one way to do it. Using trig identities, which are actually using a table, which, I'll talk about the table shortly, but if you didn't know the table and you didn't know the trig identity, you would be kind of screwed at this point, which is one of the reasons that I taught you guys from the supplement, which taught you these two formulas, which give us a different way to solve this problem. So there is a tricky identity that if you happen to know about it, it would help you solve this. I had to look this one up, but like there is an identity that says sine alpha times cos beta. This is 1/2, it's like sine of alpha plus beta. Did I write it down? What the hell is it? I didn't even write it down. I think it's sine alpha plus beta minus sine of alpha minus beta, or maybe plus here. Something like that. I don't quite remember, but I'm not going to need to remember because I'm just going to use these complex exponentials instead. So knowing this formula, this is one way to solve this problem. Or let's use complex exponentials, in which case we don't have to have any fancy freaking trig identities memorized. So, all right, let's approach this with complex exponentials. And this whole thing, okay. So this is going to become the integral of sine 2x becomes 1 over 2i times e to the 2ix minus e to the negative 2ix. Cos 5x becomes 1 over 2 e to the 5ix plus e to the negative 5 I5x, 5ix, whatever. All right. Now let's just multiply it through and see what happens. So I'll bring these factors out front to give me a 1 over 4i. And now let's FOIL this guy. So this times this is a e to the 7ix. This times this is a e to the minus 3ix minus e to the 3ix, and then minus e to the negative 7ix. Okay, now I'm going to do something which, yeah.
There's no I in the other one. So how can you take out the I?
Sorry?
So for the complex exponential you made for the cosine 5x, there's no 2i. So how can you take out the I?
This one?
Yeah.
Because everything's being multiplied. Yeah, it's multiplication. Okay, so here's something which I haven't shown you guys yet. Like what I'm about to do is an integral of complex numbers, right? Like, I guess I kind of already did it right here, and I pulled the I out in front. I didn't really justify this to you guys yet, but remember what I said when I started talking about complex numbers? Is that we want all the same rules to hold. So all the rules you know for derivatives for real numbers, they're still true for complex numbers. So just like we could pull the 2 out in front, we can pull the I out in front as well. And it appears just the same as if it were a real number. And how about for integrating these exponentials? Well, we know how to do them if they were real exponentials. And I'm telling you guys, it's the same rules. So for the real case, right, like if we had to integrate e to the, I don't know, ax, for example, we know that's 1 over a times e to the ax plus c. This is known. And I'm telling you that if a is a complex number, then this is still true. So my point is we can integrate all these guys just treating this like just the same as if it were a real number, okay? So I'll get a 1 over 4I, and then, so this will be 1 over 7I e to the 7ix, plus 1 over negative 3I e to the negative 3ix, minus 1 over 3I e to the 3ix, and then minus 1 over negative 7I e to the negative 7ix, plus c. And now I just have to simplify that. And the way the simplifying works is you look for opportunities to reapply these two formulas. All right, so that'll be a 1 over 4I times a 1 over 7I. What's that? If I combine the first and the last term, it's e to the 7I x plus e to the negative 7ix. And then I'll also have, what is it, a 3I. What do I have here? Okay, negative 3I. And then e to the 3ix plus e to the negative 3ix. Cool. So you guys see how I deliberately wrote it in that way? Plus c. I deliberately wrote the two terms with the 7s next to each other, and I deliberately wrote the two terms with the 3s next to each other, because this guy is, what is that? That's 2 cos of 7x. And this gal is 2 cos of 3x, according to those formulas. So let's see, I got a 1 over, it's a negative 28 times 2 cos 7x, and then what's that, negative plus 1 over 12 times 2 cos of 3x. So I'll get negative 1 over 14 cos 7x. Am I missing a minus sign? No. Minus, yeah, plus. I feel like I'm missing a minus sign somewhere. Am I? It's a minus. Yeah. Oh, yeah, no, it's, okay, yeah, it's. Looks good. Plus c. Okay, so yeah, that demonstrates our new method of solving integrals using complex exponentials. And you know, when you guys do your homework, I guess if it's a 7.2 problem, they want you to do it their way. When you do some of the supplement problems, they'll want you to do it using complex exponentials instead. So let me show you, let me continue with this. Let me continue with 7.2 now on one other type of integral that you're going to come upon in the homework. So I've been doing the sines and cosines all day today. Let's talk about tan and secant now in the last 5 minutes. So the key, okay, so I guess I erased it, but when I was doing all these sine and cosine problems, I wrote the Pythagorean identities in the corner because you just keep on using those. Similarly, we will repeatedly use this formula, 1 tan secretary, right? You guys never heard that? Yeah. Okay, yeah. 1 tan secretary, and let's see. ddx of tan x is secant squared x. ddx of secant x is secant tan. So it's just like you repeatedly use these guys to do integrals for tan. Let's see if I can do a few of these before we finish up today. So first one, and this is a potentially useful integral. All right, so some of these problems you may never have to use in real life, whatever you guys do. Some of them you may. You may very well have to integrate tangent at some point. Now, how do we do this? How do we do this? Okay, so this one, yeah, I'm not even going to really use this, actually. Let's write tan as sine x over cos x. Oh, and this is actually just a u substitution problem. Oh, okay, so that wasn't so bad. If u is equal to, cosine of x, so du is negative sine of x, then this is equal to negative du over u. So that's negative ln of u, which is negative ln of... Oh, I've done this already in this class, actually. Yeah, I showed this to you back when I did u substitution. I remember someone asked me what I'm about to do with this negative sign. Okay. Secant. Cool. That one's not so bad, but let me start to make it a bit harder. How about integral of tan squared? What? This is not a derivative of anything. But if we use the Pythagorean identity, which says this is secant squared x minus 1, how did this help us? Can we integrate secant squared? We can, using something I have on the board right now. Secant squared is a derivative of something. Tan. Yeah, this is the derivative of tan. So by the fundamental theorem, this is just, well, integral of secant squared is tan, and then minus x. Okay. Not so bad. How about tan cubed x? This one, I saw the book had this as an example. I was like, I don't even know how to do that off the top of my head. I think there's some trick like involving integration by parts. But you know how they do it? These sneaky bastards. They use a table. They just say, oh, this is hard, it's annoying, so just use a table. So that's what I want to point out here is there's a table for all this stuff. I don't know if you guys have used tables for integrals before. So yeah, I haven't relied on tables. Engineers probably use a lot of tables. So yeah, if you get an integral that you can't do, well, okay, I guess there's Wolfram Alpha integrator. There's also tables you can look at, and the book has tables. In fact, for all the different examples that I did today are on this table. I don't know the page number, but it's at the end of this chapter, at the end of this section. So what they would say is just see the table at the end of section 7.2 in the text. Right? Kind of a cop-out. I could derive it, but I think the point is to you guys know that the table is out there, that it exists, and to be able to use it if you need to. All right.